Okay, so picking up where we left off, we're going to keep the same model here, but we're going to change the way we're doing our numerical integration um, in a way that's commonly used in molecular dynamics, which can guarantee that the total energy of our system between the kinetic energy and the potential energy stays constant within some margin of error. And the method we're going to be using is called velocity Verlet. I'm going to call it VV for short. And we're going to start with the way that we update the position. So right now we're taking the current position and then we're adding the velocity times a time step in each dimension, the x dimension and the y dimension. The first thing I want to do is move this into a procedure. You can see that these have the same form, right? It's the current position times the velocity times a time step, and then also in the y, the current y position times velocity. So the first thing I'm going to do, I'm going to call this VV position. And this is the first time we're doing what's called a reporter. So if you have two and then a word, that's a procedure, and that's something where the agents are going to be changing their state. A reporter reports some value at the end. It's like a function, what's known as a function in most programming languages. And you can have inputs to a reporter. So in this case, we're going to have the current position, or maybe I'll call that core since it's going to be x core or y core, and then the velocity, and then the acceleration. So if we just do what we're currently doing, before we actually do the velocity relay algorithm, we would just do core plus v times dt. So we're not using a yet. If we just do our current one, in a second we'll use that. And so here we could replace, instead of doing this, we could replace this with VV position, x core, and Vx. And what this is going to do is just call this reporter. It's going to pass in the x coordinate and the velocity, and then it's going to report that coordinate plus the velocity times dt. And we can do the same thing here with the y coordinate and Vy. And this will work the exact same way. All we've done is abstract away the function for calculating the next position into this reporter, velocity Verlet position. Now, this isn't actually the velocity Verlet position equation yet. For that, we need to add one more term, which is 1/2 times the acceleration, which I'm going to add here as an input, times dt squared. And this is actually the same thing as the formula, which I can put in I'll put in the description of the video, of the position of an object if it's being accelerated with a constant acceleration. Now, of course, in our overall model, we don't have a constant acceleration. It's changing as the distance of these things changes, the force changes, and the acceleration changes. But within each little time step, you can think of that as there being a constant acceleration within that time step. And so this is the full equation for that. Now, we need an acceleration here. So I'm going to add in ax here and ay. And we're going to go up here and add that. I'm going to go ahead and put these on new lines so that they're easier to see. We're going to add an ax and an ay. And by default, they actually start at 0, so we don't need to do this. But to be explicit, I'm going to set our ax and ay to initially be 0. And okay, so now we have this movement algorithm. And now we also need to change the way we're updating our velocity. So I'm also going to do a new reporter. I'm going to call it VV velocity for velocity Verlet. The algorithm is called the velocity Verlet algorithm, but within it, there's both an equation for updating the position and an equation for updating the velocity. And here we're going to report, oh yeah, we need inputs here of the current velocity and the old acceleration and a new acceleration. You don't really need to know the details of how this works. You're welcome to go look it up. But just like you can learn to drive a car without knowing how car engines work, and you can learn to use NetLogo without knowing how NetLogo is built from the bottom up, You can use the velocity Verlet algorithm without understanding all the math behind it. Of course, you're welcome to go learn the math behind it, but don't really worry about the math at this point. I'm just showing it here so that it doesn't seem mysterious. So we're going to be reporting the current velocity, and instead of just adding the acceleration times a time step, we're going to average the old acceleration and the new acceleration. And doing this is what helps make sure that our energy stays constant and makes the whole thing more accurate. So we're going to take 1/2 times, and we're going to add the new A and the old A. So this is basically taking the average of the two. And then we're going to multiply it by dt. And so now, same thing here. Instead of using this equation here, instead I'm going to use this velocity Verlet algorithm, and I'm going to give it as input Vx, Ax, and the new Ax. And then same thing with Vy here. Vy, Ay, and the new Ay. And here, this is calculating the new Ax and new Ay. And then after we've updated our velocity, then we're going to update our acceleration to be the new one, so that next time step, the current acceleration is what it was at this past time step. Okay, and so again, this model should behave exactly the same way. All that we've done is change the details of how we are updating our position and updating and accelerating, but the model should behave exactly the same as it did before. And now that we have this, in the next video, we'll add multiple turtles interacting. And also, instead of interacting based on a spring, although you could do the same thing with a spring potential, we're going to use an interatomic potential. And then we'll be modeling atoms instead of two objects connected by a spring.